Okay. Hello, everybody. So it's nice to see you so many connected today for this COMETA Colloquium. So since COMETA is about, vector boson scattering and boson in general, I decided actually to tell you a little bit about what the future circular collider can tell you about those objects, those particles. So we'll start with a general introduction, about the future circular collider. Maybe not all of you knows about the latest development and what is the status of this project. And then I will try, if time permits, indeed, to discuss a little bit more about the physics and the physics of the standard model and the BSM bosons, right? Okay. So, what is a future circular collider? So, it's a versatile particle collider housed in a 91-kilometer underground ring around CERN. It will be implemented in several stages, like what happened for LEP and LHE later on. So, we'll start first with an E plus, E minus, X electric flavor top and QCD factories running, let's say, between 90 GeV and 365 GeV, where you can produce a pairs of top quarks. And that's usually what we call FCCEE. And then you will replace the electron and the positron by some proton to reach highest energy, maybe something close to 100 of TeV, maybe 80 TeV only, or maybe 120 TeV. It will depend a little bit on the magnet that will be available in 30 or 40 years from now. And that's the phase that we call FCCHH. And here you see the nice picture. So this little cycle here actually correspond to the LHE, and that will be really the new tunnel for FCC. It will go under the lake, it will go around the Salève, close to Annecy, and it will stay within the Seine area. So it's clear that if you want to reach 100 TeV, accelerating proton, you need a big tunnel, something like 80 or 100 kilometers. And it turns out actually also that this size is very suitable for E plus E minus collider. And there are several advantages to this big tunnel for E plus E minus collider. It's first of all that you will get enough luminosity, 5 times more than in 27 kilometer, to get sensitivity to maybe the Higgs self-coupling, the electron Yukawa coupling, or the sterile neutrinos. Something that will take, I don't know, something like 50 or 100 years in a 27-kilometer tunnel can actually be done, in a reasonable amount of time, maybe something like 10 or 15 years in a 100-kilometer tunnel. And also, it will actually make, this electrolyte factory that will produce something like 10 to the 12 Z boson, actually the best flavor factory ever, right? You will beating the rate of Bell 2 or LHEB, and it will also produce some AV meson in a very favorable kinematical environment. And finally, something that is sometimes not appreciated is that if you have a tunnel which is long enough, I mean, you can actually get transverse polarization to be available all the way to high energy meaning in this case the WW threshold. And that will be actually a crucial element, to allow for precise W mass measurement. And finally, again, if you have 100 kilometers, you can really extend the energy reach of a E plus E minus collider, probably up to 360 GeV. So you will be able to produce the top quark in pairs, and that give you some very useful information about the top, the mass of the top, about the electric coupling of the top, and these things will be very useful actually if you want to exploit all the electric data that will be accumulated at the Z-pole. If you want to do a global fit, it's better to know clearly with high precision the top mass. And that's something that you can do if you have a run at 360 GeV. So all in all, maybe after the success of the LHE, we certainly need a broad, versatile, and ambitious program that at the same time can really sharpen our knowledge of already discovered physics. So in the sense you want really a machine that has some guaranteed deliverable, improving by several order of magnitude what you already know about the structure of the standard model. So that's one aspect. And the second aspect is also that you want to be able to push the frontier of the unknown at high energy, but also at low energy. Sometimes something that has been realized that maybe the structure of new physics is not exactly the one that were anticipated before the LHE, with something which is populated the TeV scale, but maybe there is plenty of of new physics, which is light and very weakly coupled. So we need actually to find to build a machine that could also, look for this type of new physics that, by the way, can solve several deficiencies of the standard model. I mean, it could be the dark matter component. It could also solve some various flavor problem. And also what has been understood recently is that this light and weakly coupled new physics could also address the hierarchy problem, in a form, for instance, of an axion which is coupled to the Higgs field in a very particular way, in such a way that the cosmological history of the universe actually bring the vacuum of the universe to the right place with the right mass, which is somehow decoupled from the high energy unit. So clearly, together, FCCEE and FCCHH actually combine those two aspects. They will provide more precision, more energy for more sensitivity to new physics. No, it's also often said that people are excited about high energy. I mean, we are all there to discover new physics, and for a very long time we thought that new physics is indeed at very high energy. So you need to build the highest energy colliders as possible. Nonetheless, I mean, it's also true that precision is a discovery tool. By measuring with high precision the object that you already know, you can discover actually new physics, right? And there are very many different examples, in the history of physics along this line of discovery. For instance, people look very carefully about the anomalous trajectory of Uranus, and they were trying to reconcile that with the laws of Newton of mechanics. And at the end of the day, the solution to this problem was actually the existence of a new planet. Right? I mean, that Le Verrier, this famous guy, that took very seriously the equation of Newton and say, well, the only way that I can explain this anomalous trajectory is actually by assuming that there exists a new particle, or sorry, a new planet in this case. Like it could predict the mass of this planet. It could predict the position of this planet, and then he sent a letter to his friend, this astronomer friend in Berlin. And a few days later, basically, they looked in the sky and discovered this new planet. Right? So of course, I'm a little bit jealous because at that time it took only a couple of days to actually discover new physics. While nowadays, I mean, the project that we are discussing are probably will be spanning, several decades in the future. There are other examples where sometimes, you don't discover new particle, but you discover new fundamental laws of nature. And that's the case of perihelion of Mercury, that didn't obey either, the laws of mechanics of Newton. So Le Verrier again tried, to predict the existence of new planet, Vulcan. He computed his mass, his location. And in this case, his astronomer friend, looked at the sky and couldn't find any planet. And of course, we all know that the solution to this problem now is actually the understanding that mechanics don't really follow the laws of Newton, but rather, you need to expand them in the context of the general relativity. And maybe closer to us, I mean, you could also say that the Higgs boson was discovered or was anticipated ahead of time simply by looking with very high accuracy the W and Z gauge boson interaction to the quark and the leptons. This is the famous blue band plot that we're predicting with good enough accuracy, actually, the mass of the Higgs boson. And probably you can expand it along this line. There is certainly several examples along this line, right? So really precision is also a discovery tool. And in any case, when you have a good and precise machine, you shouldn't lean, or the experimentalist shouldn't lean too heavily on the series priors or prejudice. The series friend will tell you that, oh, you shouldn't look into this area because you have not discovered anything. If you can do precise measurement, you should go ahead and do that. And sometimes, you will really find very new, interesting things. I mean, maybe also the discovery of parity violation. It was not really anticipated because, gravitational interaction, electromagnetic interaction were respecting parity. So nobody expected actually that the weak interaction will maximally violate this symmetry. Nonetheless, you had, Mrs. Wu in particular had all the experimental knowledge to do this, to do an experiment and verify this. And indeed, she found a maximally violating weak interactions, right? So I think it's really also at a time where we don't have a precise theoretical guidance that we need powerful experimental tool to actually make progress. And I think FCC is certainly one of them. So the FCC project will offer an unprecedented opportunities on many different fronts. So maybe we are not, in the same situation as before the LHE or SSC, with this no-lose theorem where we knew that we are going to discover a new particle. Nonetheless, for sure, we are going, to make significant step forward in our understanding of fundamental laws of nature by probing, shorter and shorter distances, but also probing interaction at smaller and smaller couplings. Right? So now I would like to tell you a little bit about this FCC feasibility study that started, a few years ago, that as a result of the last update of the European strategy for particle physics, that concluded that an electron-positron X factory should be the highest priority for the next collider. With the longer term, the European particle physics community has the ambition to operate a proton-proton collider at the highest achievable energy. So the CERN Council actually approved this strategy, and the CERN management had to implement it. So as part of the implementation, the CERN management actually launched this FCC feasibility study that started in 2021, and it will be completed sometime next year, actually, in preparation for the next European strategy. So that's why last fall, actually, last October, we had the midterm review, 2 years after the start and 2 years before the conclusion of this feasibility study. So what was the objective of this feasibility study? First of all, to demonstrate, that it's possible actually to construct this machine. So what does it mean possible? It means that it's possible, geologically, that the CERN area is a place that can actually accommodate a new tunnel, that there is no problem with the geology, that is also technically feasible, and that there is no so much environmental showstopper. And finally, you also need to make sure that you have all the possible administrative authorization for that. Right? And so there is a lot of study that have been going on also about the cost of the machine, because you need to make sure that, CERN can build this machine and can operate this machine, within the CERN budget in particular for the operation. Right? And finally, one part of this feasibility study was also the consolidation of the physics case and the detector concept for both collider, meaning for FCCEE and FCCHH later on. So about this placement, so where to put this collider. So this is not such a trivial task, because Geneva is a very busy and complicated place. First of all, you have some natural borders with the lake, with the Jura in this area, with the Alps not that far away. And furthermore, there are also some several areas that are protected because of the environment, right? So it was really a tricky part actually to find, where really to put this collider. There is various things that have been optimized, optimization in terms of the surface constraint, the land of availability, the access of road, etc. The environment, the infrastructure, how to bring the water and the electricity and the transport which is needed. And finally, how to have a machine which is performant enough, right? And at the end of the day, so there have been about 100 placements that have been considered, and things have been optimized. And finally, it was concluded that the best lowest risk baseline is something around 91 kilometers with 8 surface points that will allow you actually to have 4 interaction points and 4 other access points, for technical usage. So here you can see actually how things have been going on in terms of discussion with the various communes that will host these tunnels. And this is a plot from last June. And by now, actually, I think all the communes have been discussed with, right? And finally, there have been also some interesting study that have been going on to understand a little bit better actually what is the composition of underground land. In particular, you want to make sure that you won't encounter water, because water is actually a problem when you want to dig a tunnel, right? So there are various things that have been going on the surface, also on the lake, because at some point you might have noticed that the tunnel will go under the lake. So that's why, for instance, it cannot go too far in the direction of Lausanne, because the lake is becoming too deep, and you will have you will need it to dig too much deeper if you want to have these colliders. So that's why you need to remain close enough from Geneva. Anyways, these things are going on, and we get a better understanding really of the underground structure, right? Then there is also an important thing is that, this collider need to be accepted by the local population. And, in particular, what are you going to do with the excavated material that will represent something like 3 million of meter cube, right? And the idea is actually to reuse this excavated material, and there have been interesting studies, to actually make this excavated material fertile enough. For instance, with mixing this excavated material with some fungi that will make it usable even for agriculture, if not for forest, right? So that's one aspect, really, what to do with this excavated material. And the other aspect is actually what to do with heat that will be produced when with the collider will be running, right? So clearly there have been some studies of how to distribute the heat into local houses or local schools or swimming pools, etc. Hospital also. But there is also the aspect of what are you going to do, for instance, during the summer, when the houses don't need extra heat. Instead, there are some consumers that need heat all year around, which are, for instance, the cheese factories, in particular in the Jura or Haute-Savoie. There are many of them, and they express high interest actually of getting in touch with FCC to really collect the heat produced by these colliders. About the infrastructure, the local infrastructure, clearly, you don't want to destroy the nice landscape around Geneva, by building high or many highways or whatever, bringing new electricity line. And that's why also, you needed to optimize the placement, in particular of this access point or whatever. And it was concluded that at the end of the day, for a tunnel of 91 kilometers, you need to build less than 4 kilometers of new departmental road to have access to these colliders. Right? So it's really a very nice environmental study that have been going on. And finally, also the connection to the electrical grid. Certainly, you don't want to have a nuclear power plant, just to fuel this collider. So you need to make sure that it will be nicely integrated in the existing electricity grid. And also you want to make sure that, by switching on the collider, you won't switch off all the electricity in Geneva or in Page X, right? So this has been studied very carefully, by this French electricity company, and was concluded that everything was fine. You can really provide electricity also in a redundant way, in such a way that you can anticipate some electricity blackout without affecting the operation of the machines. Finally, there are also some consideration of the civil engineering. Building a 91-kilometer tunnel is something which is not easy, even though is nothing comparable really with a tunnel for road or for railway. I mean, it's much smaller circumference of the ring itself is something like 3.8 meters in diameter, also for the tunnel. Nonetheless, I mean, you need to plan ahead. You will have some tunnel boring machine that will brought down in each of the access point, and they will be moving at the speed of 80 meters per day in the morass where you will dig this tunnel. So this means that you will need something like 8 years actually to completely dig the tunnels. Right? At the end of the day, we will have, as I say, 4 interaction points, and there will be 2 large and 2 small caverns. So the small caverns actually are of the size of the CMS cavern at the moment. So it's not that small, but still, I mean, something quite sizable. And then the large cavern will be able to accommodate later on, in particular, the FCC HH detectors, right? That will be bigger than the LHE ones. And here you can see, for instance, a complicated Excel sheet to really plan the work ahead to make sure that you dig the tunnel in time, and then you can deliver the tunnel to install all the detectors and also the accelerators clearly. So this, as I say, concluded in this midterm report that was produced a year ago, about a year ago. So it's a 700-page document constructed along 7 chapters, because the cost and financial feasibility actually is a little bit more secret, so it will be in a separate document, and there are in additional some references. Right? So the 7 chapters are about the placement scenarios, the civil engineering, the implementation with the host stage, the technical infrastructure, the FCC EE collider design and performance, the FCC-HH accelerator, the physics and experiment, and then the references. Of course, nobody is going to read this 700 pages document. So, in addition, we have been asked to produce a summary, an executive summary of 44 pages. But even 44 pages, is usually a too large document to be read by any committee which is actually going to take a decision about this future machine. And so every committee, that reviewed this document actually produced another document, another summary, which is half of the size of the previous document, to end up into, a very executive document of 1 or 2 pages that the important people can read off. So this feasibility midterm report have been reviewed by the Scientific Advisory Committee and the Cost Review Panel in October last year. Then the Scientific Policy Committee and the Financial Committee met in November. And finally, the CERN Council met in February this year and reviewed these things. About the structure of what concerns the physics experiment and detector, which probably you're all more concerned with, and the environmental aspect or the accelerator aspect. So there were 3 main deliverables: the documentation on specificities of FCC-EE and FCC-HH physics case, the strategic plan for the improved theoretical calculation, and finally, what are the detector that you should build to actually, accumulate all the data that correspond to the collision that you can expect, the collision rate that you can expect at this collider. And at the end of the day, 60 pages were expected for this physics chapter, but at the end of the day, we were a little bit carried away. So we produced something like 110 pages that are organized along these 3 main deliverables, right? And the topics that are covered actually are FCC-EE, which is much more than the X factory. It's really a precision for discovery. And it was also discussed what you can actually discover directly, by producing so many Z bosons. And finally, there is the aspect of X and electroweak, and all the flavor factory aspect of FCC-EE, and finally a chapter about FCC-HH, the exploration of the unknown at the highest possible energy. And there were a chapter really discussing also this complementarity between the 2 machines, why, for instance, it's important to have an electron and positron machine before going to hadron machines at higher energy. So as I say, this report has been reviewed by various committees, and they all express very positive opinion. In particular, the CERN President Council, Eliezer Rabinovici, said it was the first time really that I hear the financial committee saying that you shouldn't care about the money, you should really go for the physics, and we'll try to find the money to really build this collider afterwards. Right? Finally, the US also expressed some intent of contributing to FCC-EE if it is actually declared feasible by the CERN management and the CERN Council. Right? There has been a nice ceremony in April at the White House where Fabiola Gianotti, the CERN director Gianotti, signed this US statement of intent with the chief technology officer from the White House. Right? Also on the EU side, there have been some strong support. In particular, the last one comes from this EU competitiveness report produced by Mario Draghi in the beginning of September, where, for instance, you can find some very nice statement of supporting CERN and supporting FCC. That really, this is a project for the future to maintain some leadership in Europe in particle physics. And even at the 70th anniversary celebration of CERN a few weeks ago, Ursula von der Leyen really concluded that CERN has become the center of the world for particle physics. And she was proud that the EU has funded the FCC feasibility study, and they want to continue along these lines, right? So what is the way forward? So this is the timeline of the project, and you can look in a little bit about the date, but really the bottom line is that we are only 20 years away from the first collision in the EE machines, right? So of course, there will be a lot of things happening in those 20 years. First of all, there will be some expression of interest that will be submitted for the European strategy update, sometimes next year. Finally, the CDR for the various detectors are expected in 2031, the TDR in 2035. The installation of the detector will start, after the tunnel is fully dug, so it's sometimes in 2041, and finally the commissioning should start in 2045. So again, 20 years away from the collision. So let me now discuss a little bit what kind of physics can be done, right, at this machine. And you can understand that by simply looking actually at the luminosity plot as a function of the center of mass, something which is very characteristic of the circular collider as opposed, for instance, to linear collider. So here at the circular collider, the luminosity actually increases when you decrease the energy, meaning that you can really accumulate a lot of data at low energy, in particular at the z-pole. So something like 10 to the 12 or 10 to the 13 Z boson will be produced, in a couple of years. So put it in another perspective, I mean, the LEP1 data will be accumulated every second minute when FCCEE will be running, right? So something that took 10 or 15 years at the time of LEP, can be done now in a few minutes. And then, since it's so fast, you will have exciting and diverse program with different priority every year. It's not that you need to wait and to run the machine 10 years or 15 years at the Z pole or at the X pole to understand those objects. You can spend a couple of years at the Z, then you go to the X, and then you go back to the WW before going to the TT bar threshold, right? By the way, the order of the different stage is still subject to discussion on optimization. It's clear, for instance, that you will need to run at the Z pole at least to calibrate your detector, to calibrate the machine, etc. But again, you don't need to do the full 2 years of run at the Z pole. You can simply spend a couple of days, a couple of weeks, and then go to different energies and then go back. For instance, when you have understood exactly how your detector works, you can go to the X threshold to produce the X, to study the X, and then you realize that, oh, maybe I'm missing some information about the Z, so you go back to the Z, etc., etc. So there is a nice optimization that is being discussed at the moment, right? So to give you some perspective of the number of events that you can expect, so as I say, you will be spending a couple of years at the Z pole, 1, 2, or 3 years, to accumulate something 6, 10 to the 12 Z, maybe 10 to the 13 Z. Then you could also accumulate something like 10 to the 8 WW pairs, and about 1 million of Higgs boson produced in association with the Z, but also produced actually by W fusion, right? And the number of W fusion event is actually growing with the energy. So you will double the number of W fusion X produced, when you go to 365 GeV, where you will also accumulate something like 2 million of top quark pairs. So yes, you will achieve a super statistics, in a very limited amount of times, right? So now that you will produce something like 10 to the 12 Z boson, so you can expect a statistical uncertainty of the order of 10 to minus 6, right? But there is a lot of work to be done, really, to exploit all this statistical uncertainty and make sure that you are not really dominated by systematics. So this means that, for instance, you need to develop Monte Carlo generator, software and computer, detector requirement, detector concept, control analysis, lattice simulation, theoretical calculation, polarization and monochromatization of the beams, machine detector interface. These are all aspects that are still being considered at the moment, really to build the best possible detectors, to really achieve the precision that you can hope for statistically. So another way to present the physics program is really along these three main directions. So it will be a X factory. So certainly you will accumulate a lot of data on the X. You will reach 365, so you will become a top factory, where you can learn about the mass of the top, the width of the top, but also all the electric coupling of the top quark itself. And finally, it's a big advantage, it's a big difference compared to the linear collider. You could also accumulate immense statistic at the Z-pole, right? So you will have an intensity frontier machine that has several advantages. For instance, you will learn about electric and QCD, about the mass of the Z, the width of the Z, the effective numbers of neutrinos, all this electric precision measurement, RL, or this forward-backward asymmetry, etc. But also on the QCD side, you will learn the value of the strong gauge coupling with a per mil accuracy. You will also improve the knowledge of quark and gluon fragmentation function. You will get a clean, non-perturbative QCD studies, in particular if you run the machine below the Z poles, right? So that will certainly complete the standard model itself. But since you will be producing so many Z bosons, you could also explore some rare decays of this Z boson to directly search for light new physics, which will have a weak coupling to the gauge boson, to the standard model gauge boson. And from there, you can learn about axion-like particle, dark photon, heavy neutral lepton, also some long-lived particles, that will have a very tiny coupling to the Z, but since you are producing so many of the Z, you will finally improve really the sensitivity to these small couplings. And finally, the third aspect of this intensity frontier machine is actually that you will be producing with high statistics, heavy meson or even tau leptons, in a number which is much higher actually than what can be produced in current and future flavor factories. So this means that you can improve the knowledge of B physics, and you can improve the knowledge of tau physics. For instance, you can perform electric precision observable using the tau leptons. You can perform some incredible test of the lepton universality violations. Right? And on the B physics side, you will improve, for instance, the knowledge of the CKM element. You will probe CP violation in neutral B mesons, or you will also search for flavor anomalies, for instance, in the B2S tau decays and things like that. But of course, I mean, these are some topics that you can expect to do, but to achieve this physics program, you also need to build the good detector which is more appropriate. For instance, if you want to do some fantastic electric and QCD measurement, you need a good particle flow. You need a good energy resolution, a good particle identification. If you're interested instead of direct search of elusive physics, you need to make sure that your detector is hermetic enough, that you have a good tracking, good calorimetry also. And finally, if you want to do flavor, you need a good momentum resolution, a good tracker, a good vertexing, a good tagging, and energy resolution, hadron identification. So all these things are being quantified at the moment, really to make sure that you understand and that you understand the detector that you want to build in a few years from now. So here, again, this is the baseline plan for this FCCEE. But in addition, there are also other opportunities, that will come. For instance, you could run this machine at 217 GeV, and 217 GeV is actually the threshold for the ZH production. So this way you can really look at the threshold production, and you can learn with high accuracy the X mass. Right? Of course, the X mass you can also already measure with great accuracy in ZH production, away from the threshold. Nonetheless, it's good to have an independent with different systematic uncertainty. At this level, you really have to take care of the systematic uncertainty, and having some redundant measurement is always a nice aspect. Another very interesting energy is actually 125 GeV, because this is just the mass of the Higgs boson. So this means that if you run this machine at 125, you can really hope to be able to produce the Higgs boson as S-channel resonance simply by the collision of an electron and positron. And this will give actually a unique access to the electron-Yukawa couplings, right? So this is the only machine that will have enough luminosity and enough precision, enough calibration on the beam energy, for instance, to measure this electron Yukawa with a sensitivity which is close to the standard model expectation. And finally, you can also run this FCC collider below the mass of the Z to perform some QCD precision studies, in particular in the non-perturbative regimes. Right? So this what concern actually the collider physics, but you can also exploit FCC facilities in a different way. For instance, you can use the electron from the injector from beam dump experiment, or you can extract the electron beam from the booster, and you can reuse the synchrotron radiation photon to actually make FCC the best light source machine that will be producing, a photon in the 50 or 100 kV regime in a rate which is much more abundant than what you can be doing at any other light source facilities. Right? So there is a large program which is being developed at the moment, which is being looked at, and there is even a nice workshop sometimes in October, sometimes in November, in a few weeks from now, and you are all invited to follow these things if you want to learn what a collider can do for non-collider physics. But as I promised, I mean, because that's the theme of this COMETA network, I should also tell you a little bit more in details what actually FCC can do for what concerns the standard model and the BSM boson. So this means that I will be talking about the X, about the Z and the W. I will also say a few words about dye boson production as a way to actually improve the measurement of the triple gauge coupling. And then I will say a few words about axion and AV scalars. So I left out some topics that I don't have time to cover because they're also not directly connected with COMETA topics. And you can look at the slide in the backup about flavor physics, about AV neutral lepton, long-lived particle, about supersymmetry, etc. So about the Higgs bosons. So Higgs, the standard model Higgs at FCC will be produced mostly at 240 GeV, where you have a peak of the cross section. And then at 365 GeV, where you have additional event because the WW freshen actually is picking up at this energy, and you are expecting to produce about 2 million of Higgs boson at 240 GeV and 300,000 events at 365 GeV. But actually, by combining those two events, you can really improve the knowledge of what you can achieve only if you were running only at 240 GeV. For instance, here I gave you some number of the improvement on the knowledge of the X-half coupling, the knowledge of the X coupling to the W, to the B quark, etc. When you combine the two run compared to what you can achieve if you run at a single energy, for instance. So if I had to summarize a little bit, the X physics at FCCEE, I will say that it will provide an absolute normalization of the coupling by the famous recall method, that with high accuracy the energy of the beam. So from that, you can really study the X coupling without actually having the X to decay. So it will certainly goes, much beyond what LHC can do, because LHC fit doesn't converge without making any assumptions. He will, in the sense, he will provide a direct measurement of the X width by, again, looking at the Z recall with an accuracy of the order 1% and measurement of the X mass with an accuracy of 3%. And here you have to compare with, for instance, what is known currently or what will be known at the end of high luminosity LHC, by an improvement by more than one order of magnitude, basically. So you will have a model-independent coupling determination with an improvement factor up to 10 compared to the LHE. This means that you have an indirect sensitivity to new physics up to 70 or 100 TeV, at least if new physics is maximally strongly coupled, right? So just by looking at the deviation, you get the scale of the new interaction, and you can convert that scale in terms of the mass scale of new resonances, for instance. And finally, you have a unique access to the electron Yukawa, something that cannot be done in any other machines. So for what concerns the mass of the Higgs boson, again, it is mostly determined by the recall mass in the Z lepton-lepton X event. And there have been thorough studies of the detector design impact. There is a nominal sensitivity of the order 4 MeV, which turns out to be actually the natural width of the X in the standard model, and you can achieve that, but there is way to go beyond this nominal configuration, for instance, by increasing the magnetic field or by involving some lighter tracker with silicium. You can really getting better things. So these things have been documented, and there is notes that have been produced, and they are compiled in the feasibility document that is being written at the moment for this European strategy update. So FCCEE will also give you access to the hadronic decays of the Higgs boson, something which is sometimes a little bit difficult at a hadron machine simply because of the background. And here you can actually reconstruct most of the hadronic decays of the Higgs that at the end of the day count for about 80% of all the decays of the Higgs. Right? Yeah, you will have a solid measurement already of the coupling of the Higgs to the second generation of quark, and you have interesting process also for prospect for the first generation and FCNC decays. Right? So looking at decays of the Higgs that violate flavor, that yeah, something which is interesting that you can achieve when you have good flavor tagging in particular. So I wanted also to say a few words about the coupling of the Higgs to the electron, because at the end of the day, what really matters to understand nature around us is to see whether the Higgs is indeed responsible for the mass of the particle, the mass of the particle that matter is made of, not only about the top quark. That's something that the LHC has been established. There is no doubt that the Higgs is responsible for the mass of the top, of the bottom. But for what concerns the mass of the first generation, or even the second generation, things are a little bit less clear. And in particular, it's important to verify that, in order to see what we can say about the generation of flavor. Why an electron is so much different than a muon, has to do with the Higgs coupling, and we need to understand whether or not this Higgs coupling actually follows the standard model predictions. Right? So as I say, the way to test this electron Yukawa is by producing the Higgs as a S-channel resonance, and here you can see actually the Brett-Wigner peak. But of course, in reality, there is initial state radiation, there is the spread of the center of mass energy of the beam, etc. So the bump that you can expect is actually reduced. Nonetheless, with the luminosity that can be accumulated at FCCEE, the total cross-section taking into account this effect will be of the order of 300 attoborn, and this is something that that will remain visible at FCCEE. Namely, that if you run at 125 for a couple of years, you will be able to reach really the sensitivity predicted by the standard model. Right? But to do that, you need to make sure that you control the energy of the beam, and in particular, there is this particular operation mode, which is called monochromatization, where there is actually anti-correlation between the energy of the positron and the energy of the electron, in such a way that the beam energy remain more or less equal and always the same. Right? So this is something which is being investigated at the moment, with experimentalists, and there is good prospect actually that it will work, and it will be a big improvement in the operation of the colliders. So the way you want to search for the Higgs which is produced by E plus E minus annihilation is actually by looking at decay channel where there is basically no background. In particular, you want to be able to disentangle an Higgs from a Z boson, and for that, it turns out that it's best to look at the decays of the Higgs into two gluons. And here you can see the table that have been produced, and indeed, with 10 inverse attobarn, you can expect something like 55 signal event out of a background of 2000. So you will reach more than 1 sigma sensitivity in the existence of the electron Yukawa. And then, of course, if you include more IPs, and if you increase the luminosity, then you can hope to reach 3 sigma or even 5 sigma if you run long enough. Right? And this also triggers some interesting work on the theoretical side. There have been a recent phenomenological study that shows that the transverse spin asymmetries can actually increase the sensitivity to the electron Yukawa. right? So that's something that cannot work actually for the decays into gluons, but that can work for the decays into BB or WW, because then you have some interference between signal and background, and you can actually see really the enhancement of the spin asymmetries can be used really to increase the sensitivity in the electron Yukawa. So that's something interesting, that still need to be investigated a little bit further, in particular, with full simulation and things like that. Yeah, to get the final word. And basically, the goal here is to understand whether it's worth or not to spend a couple of years dedicated at 125 GeV to really extract this information about the electron Yukawa. So something which is not foreseen a priori in the design baseline, but that's something that could be added or could replace something else. I don't know. So that's something that people are discussing at the moment. Finally, I also wanted to say a few words about the determination of the Higgs self-coupling. Traditionally, that's the way it is done at the LHE, or will be done at the LHE, at high luminosity LHE, is to look at the pair production of a Higgs boson, because then you are directly sensitive to the Higgs self-interaction, the cubic self-interaction. But it was also noticed actually that the same a similar sensitivity on the Higgs self-coupling can be reached if you measure with enough accuracy all the single Higgs production channel when you are becoming sensitive actually to the radiative correction. For instance, at the LHE, here you will have TTH production that at one loop will involve actually these Higgs cubic couplings. And the same is also true at lepton colliders. You can look at double Higgs production, but for that you need to reach enough energy, something like 500 GeV. Or if you remain at low energy, below 500 GeV, then you can still actually gain sensitivity to the Higgs self-coupling, for instance, by measuring with great accuracy the ZH production cross-section. So since the expected experimental sensitivity will be of the order of the per mil in the measurement of the cross-section, you can see that actually you will get a sensitivity of order 1 directly on the Higgs self-coupling. And if you put the numbers, with a combination of different energy run at 240 GeV and 365 GeV, you can really hope to disentangle actually a modification of the ZH cross-section, which is due to the Higgs self-coupling, from another modification that will be due, I don't know, to the interaction of the Higgs with the Z, simply. And you can really pin down exactly what is the value of the Higgs self-coupling with an accuracy around 20%, basically, right? So something maybe similar to what high luminosity LHE will achieve, but you will do it in a totally different way, so with totally different systematics. So that will be some added value clearly in this extraction of the Higgs self-coupling at FCCEE. Okay, this is a final plot using the latest luminosity, and you can really see by the combination of the various run what constraint you can gain. You can also ask yourself, what will be now the added value of FCCH8 for what concern Higgs physics, right? Well, the answer is simply that FCCH8 will be really a truly Higgs factory. At FCCE, you will be producing about 1 million of Higgs boson, but at FCCH8, you will be producing about 1 billion of Higgs boson. So this means that you will gain sensitivity to the exotic or rare decay channel of the Higgs boson. And you will also be producing the Higgs in extreme kinematical region. For instance, with a PT larger than 1 TeV, you will still be producing about 1 million of Higgs boson. Right? So certainly you will learn greatly about the Higgs also at FCCH8. I wanted to say a few words about what we'll be learning about the W and the Z. So here is this typical table of the sensitivity on electric precision observable, the current precision and the statistical uncertainty which is expected at FCCEE, that has to be compared with the systematics, right? So for instance, just to give you an order of magnitude, you will be limited by systematic at the level of 100 kilo electron-volt in the determination of the mass of the Z, about factor 3 larger for the mass of the W, right? But something which is certainly mind-blowing and an order of magnitude improvement compared to the current knowledge, right? Yes, about some example of electric measurement that will be performed at Terra Z. So you will be looking at E plus E minus goes to a pairs of fermion, and you are interested in the interference between the photon and the Z contribution, because that, for instance, will give you access to the value of alpha electromagnetism with a great accuracy at the level of 10 to minus 4, 10 to minus 5, something again which is larger than, I mean, uncertainty which is much improved compared to the current knowledge. About the mass of the W, something that attracted a lot of attention at LHE 1 month ago. So here you will also improve by 1 order of magnitude compared to high luminosity LHE. And the advantages is that now you will have 2 independent ways to measure the mass of the W. First, simply by looking at WW threshold cross-section, where you can measure the mass of the W, but also by looking at the decay product directly of the W, right? And both of them will reach an accuracy, sensitivity, which is comparable to the value that you will obtain from electric precision observable fit. So this means that you can really have a test of the closure of the fit of the electric precision measurements. And here it's another way to really illustrate the precision that you will reach at FCC. So this is the ellipses, of S and T at high luminosity LHE, and here down there, this little point here is actually what you will be achieving at FCC EE, right? So indirectly, clearly, you can use this electric precision measurement to probe indirectly the sensitivity to new physics up to a scale of the order of 70 TeV, provided, of course, that new physics is directly coupled to the X and the electric sector. But actually, even if you have new physics which doesn't talk directly to the W and the Z, you integrate out this particle, you will produce interaction, for instance, among 4 quarks or 4 leptons. At the mass scale of this new physics. And then you can ask yourself how this new physics actually mixed with operators that actually contribute to the electric precision observables, right? Just by the running of the renormalization group. And this is an exercise that has been done by Matthew McCullough and his collaborator a few months ago. And they really show that even if you have some new particles that don't directly couple to the W and the Z, still indirectly via some quantum effect, you can actually put some bound of the order of a few TeV on these new particles, right? So that really shows the power of electric precision measurement, to indirectly probe new physics. So the Terra Z program gives really a comprehensive coverage of new physics coupled to the standard model. If a signature shows up elsewhere, it will also show up at the Terra Z. So Terra Z is not just a high-power LEP exploring electric sector. It can really directly, or indirectly in this case, probe new physics. Right? About dye boson production, something that is usually a concern for people involved in COMETA. Well, the advantage of dye boson for new physics is that actually you will have a look, you can look at the tail of the distribution, for instance, a large PT, and this is usually where the effect of new physics show up over the background. I mean, under this dogma that energy really helps accuracy, because the background will fall down with the energy, but a new physics will remain constant, or will even increase with the energy. But of course, this requires high statistics, and this is exactly what FCCHH actually is producing. So for instance, here, I looked at some numbers of W produced in association with the X, assuming or requiring that the X has actually a PT which is larger than 500 GeV. And you can see how the numbers evolve. I mean, from, for instance, what you will accumulate at high luminosity LHE and what you will obtain at FCCHH. So there are something that is not feasible at all. For instance, looking at WH when the H decays into 2 photons, you simply don't expect any event at high luminosity LHE, where you will expect something like 1,000 of event at FCCHH. So this is something that finally can be seen, can be exploited to learn, for instance, about the triple gauge boson by simply looking at this channel, right? So these are 3 different channels that we have explored. WH when the H decays into 2 photons, ZH, again, when the X decays into two photons, or also in this case, some hadronic event, where usually you are swamped by background, in particular at LHE, but you can hope to see something at FCCEE. So there have been some combinations. So precisely, there are those two different channels, WH and ZH, are actually sensitive to different operators that are acting on different triple gauge couplings. And then by combining those different channels, you can get a global picture. For instance, this is a fit of what you can expect at FCCEE and FCCHH by really looking at this association production of a gauge boson with a photon. Right? So again, is several order of magnitude improvement compared to the current knowledge at LHE or the future high luminosity LHE. And you can also compare, the sensitivity along compared to what exists at the time of LEP, and here you can see again 2 or 3 order of magnitude improvement. There is even sensitivity to the interaction that are violating CP, so something a priori which is constrained by the measurement of EDM. So here clearly the collider measurement won't be competitive with this indirect EDM measurement. Nonetheless, it's also complementarity information and different systematics and I mean wild exploration, because at the end of the day, the EDM are measuring only one particular direction in the parameter space of all possible operators. And here, clearly, you can pinpoint individually each of the operator at FCCHH, right? So there are some value, even though if you do a fit for one operator at a time, clearly EDM will overperform collider physics. Yeah, about BSM, so just to flash maybe, because time is running, just to flash the opportunities in the discovery of ALP, this axion-like particle. So clearly, if you look at ALP, for the ALP that are very light, I mean, there are very tight constraints coming from astrophysics and for cosmology. But when the mass of the ALP is of the order of 1 MeV or above, then it turns out that actually the astrophysics constraints are fading away. And then you can really see interesting limit coming from collider experiment, also from beam dump experiment. But here, if you want to compare the beam dump experiment for FCCEE, you can see really the advantages of this collider, in particular, to look and to search for axion, which will be produced in association with a photon or with the Higgs bosons, right? So this is a diagram, for instance, that you can hope to see at a future collider. For AV scalars, I mean, for instance, I don't know, the AV scalars that exist in 2x doublet model or in supersymmetric model, there are some bounds of the order of 1, a couple of TeV at LHE or future or high luminosity LHE, and you can see here the new bound that you will be expecting at the end of FCCHH. So basically, again, improving by a factor 10 compared to the existing bound, either for the pseudoscalar or the charge scalars, AV Higgs bosons. Right? So time is running out, so let me conclude. So LHE really changed the landscape of high energy physics. There have been a Higgs discovery and nothing else, or maybe nothing else yet discovered. So it means that maybe the structure of new physics is different than what people were thinking for a long time, and you really need a new machine which is broad and versatile that can explore high energy but also light and weakly coupled new physics. So the experimental analyses have been smarter than initially thought, and maybe one inverse autobahn in 2024 is actually much more valuable than one inverse autobahn in 2028 when the LHER started. So maybe we shouldn't wait 2041 to switch off the LHE and to start FCCEE. So a circular X factory like FCCEE has a rich potential. It's a quantum leap in testing the standard model, but it has also great potential to search directly and indirectly for new physics. And FCCEE is an essential part of an integrated program to probe the high energy frontier. FCCEE is a project that perfectly fits the need of high energy physics after the LHE. It has guaranteed deliverable and a broad experimental program. So we have profound questions and we need to create the opportunities to answer them now. And for sure, FCC will contribute there. Okay, thanks a lot.